acylation reactions. So acylation is the addition of acyl groups to molecules, and this can be achieved through reactions of acid chlorides and acid anhydrides. Theoretically, acyl groups can be added by reactions with carboxylic acids, but in reality these reactions are going to be slow and inefficient. So let's have a look at the reagents we would use here. This is an acid chloride, it's got 2 carbons, so this is ethanoyl chloride. And this here is ethanoic anhydride. There's a special case to consider as well that you may have met before if you've already studied benzene chemistry, and the special case is if we are doing acylation of benzene, we actually need a particular catalyst. So here is our ethanoyl chloride, and we're adding this group here, and also producing HCl, and the catalyst in this case is aluminium chloride, and the product is phenylethanone. So that's just a short reminder on the benzene chemistry there. So let's have a look at some acylation reactions with acid chlorides. There are 4 of these that you need to think about. There is the reaction with ammonia. There is the reaction with a substituted amine, such as a primary amine. There is the reaction with water and the reaction with alcohols. So let's have a look at the ammonia first. The product that we get there is an amide. In this case it's a primary amide. If we're going to use a substituted amine to do this, we're still going to get an amide, but it will be a substituted amide. So the R group is on the N here. So an N substituted amide. We get carboxylic acid. If we react with water, then we get carboxylic acids, and if we react with alcohol, we get esters. But in this case, we get a byproduct that is formed from this going. So the byproduct of all these reactions is HCl, which is a pretty nasty byproduct to deal with. If we look at the same reactions with acid anhydrides, we get the same products. Again, amide, N substituted amide. Here we're going to get an ester, and here we're going to get a carboxylic acid. You can fill in those structures. The byproduct in this case, though, comes when this whole part of the molecule is lost. And the byproduct in this case is a carboxylic acid. Which is easier to deal with. Let's have a think about the mechanism of this, and in this case we'll look at mechanism with ammonia and ethanoyl chloride. So we start off with our ammonia, remembering our lone pair. Nucleophile goes in. Let's have a look at what's formed as a consequence of this. We have our O- with our lone pair. Being careful to remember that the nitrogen has now got a positive charge on it, and this will then react with an excess of ammonia, which will act as a base, take away this proton here. This electron density will take care of that positive charge. At the same time, this lone pair here in the oxygen is coming back in to reform the double bond, and the chlorine is leaving. So this is quite a lot of arrows happening at once, and the product of this is our primary amine, which is called ethanamide. So we're going to think about how you might mark this and things that you need to remember. This one's 2 arrows. Careful with the lone pair on the nitrogen. There's a tendency to mess that one up there. Remember on this one, plus and minus on the structure. Four arrows. Quite often this deprotonation arrow, the use of the ammonia isn't credited, but it is worthwhile learning it just in case in the future it is credited. May also ask you why a excessive ammonia is being used. So in your handout you've got some examples for you to try, and if you just pause the recording at this point, then you can have a go at those and then check yourself. Let's run through these mechanisms now. Drawn our primary amine with its lone pair. In it goes, out into the oxygen. Remembering our minus charge on our oxygen now. Okay, so now we're going to work on removing these charges. Although it's not often credited, we're going to draw that it's the primary amine that's going to take a proton. In comes the lone pair from the oxygen, and out goes the chlorine as a leaving group, leaving us with okay, and we could try and name that 1, 2, 3 here. So 3 is our longest chain, based on propanamide, and it's N substituted, so N-methyl propanamide. Okay, the next one, this is ethanol chloride with ethanol. So we need to draw out our alcohol such that it shows our lone pair. That we're going to use. In it goes here, out into the oxygen. In this case, our oxygen has the positive charge here, and we've got another oxygen with our negative charge here, and our ethanol itself is going to act as a base and remove the proton. to reform our carbonyl group and remove our chlorine as the leaving group Cl-, leaving us with ethyl ethanoate. The next one, we're going to look at the action of water on this anhydride, which is a linear butyl-based anhydride. Draw out our water such that it shows the lone pairs in to here, out into our oxygen. Remember our positive charge here and our negative charge here. In this case, we are going to again use another water molecule to act as a base and remove a proton. Electron density coming back in here. The lone pair on our oxygen is coming in to reform our carbonyl group, and we're now going to lose this group. We'll have a look at what that looks like. Here's our product. So butanoic acid. Look at what we lost, which was this bit here. We lost this ion, the butanoate ion, which in reality will become butanoic acid. And thinking about the name for this overall reaction, the name of the mechanism is nucleophilic addition elimination. And that applies to all of these mechanisms because you have the addition of a nucleophile followed by the elimination of these leaving groups here.